Good morning, everybody. Right now, we are going to start our chapter 9 again. Chapter 9, Subroutine and the Control Abstraction. This session is week 6, session 2. We are on Subroutine and Control Abstraction, and we are on part 2 of this chapter. In this part 2 session, we pretty much on some special function call. And the first thing that I would like to talk about is this exception handling. And what is exception? Exception is something occurred that needs special treatment. So what is exception? Exception is a hardware detected runtime error or unusual condition detected by software. And this software actually means the Java virtual machine or the system OS. Usually, these two software are the software that reporting these unusual conditions, such as the overflow of the arithmetic, or array index out of bound, or you have the end of file on input, or you have wrong data type when you key in from console. These are the typical conditions that will happen in your software while you are executing a certain program. And actually, the exception can also be user-defined condition. It not necessarily be an error, but it can be something that you use to handle special cases. For example, if your software is not well written or is not completed, or you know that there is certain memory limitation, such as you are short of memory for some reason that you already know this software will go into that situation, then you can define certain condition and throw some exception, even though the system may not be whole, and your program may still be able to run by itself. You still can define some certain user-defined condition to handle the exceptions. Exception handling. What is an exception handler? Code executed when exception occurs and may need a different handler for each type of exception. So exception handler actually is some function, and usually this function is written so that you can use that to handle these exceptional cases. But before we have this exception handling mechanism, actually, programmers need to handle it by themselves. They need to know about why might went wrong and prevent that to happen in your software. So exception handling is an add-on mechanism on the modern day languages to handle these situations that might create errors. So why design in exception handling facility? It will allow users to implicitly handle errors in a uniform manner, allow users to handle error without having to check these conditions explicitly in the program everywhere they might occur. So actually, you write the exception handling mechanism in somewhere, and you can use that over and over again. Exception handling is a special subroutine code. So that's why this exception handler is put in this chapter 9, subroutine and control abstraction. So problem may occur, and then your virtual machine may create an exception and throw it, and your program need to handle it. And these are the 4 steps of the exception handling mechanism. And some older day programming language like C, they don't have this exception handling. But modern day C++, C++11, Java, C#, Python, they all have the exception handling mechanism. And this chapter and this lecture we will be talking about this exceptional handling. And we also have another lecture on this. So we have part 1 talking about exceptional handling, and part 2 talking about the catch, try, catch, and finally blocks. Workarounds. If we don't have the exception handling routine, then what can we do? To cope with such error without an exception handling mechanism, the programmer has basically 3 options, none of which is entirely satisfactory. First, invent a value that can be used by the caller when a real value could not be returned. So this actually is similar to the unit test or software testing. Sometimes if your code is not completely ready and actually you are developing certain software and you try to test the software in a larger scope, then you may have to invent some value to help the testing. Or you can use this exception handling, you can invent your own exception handling mechanism to handle it. To invent a value or something to replace the response of your own software, sometimes it's called mark or stop. Number 2, return a implicit status value to the caller. If you cannot make up a value to be returned, then you can still do another thing, that you report a certain status value. Who must inspect it after every call? The status may be written into an extra explicit parameter stored in a global variable or encoded as otherwise invalid bit pattern of a function's regular return value. So this is another way to handle it, that you just report what status you have, and then your own program need to handle it. So this is kind of similar to the exception handling routine, that you throw some object, such as the exception object, and then you have the exception handling routine to handle it. And this is similar, but in the old day, if you write C program, you can actually report some status, and your program need to handle on it. Third, relying on the callers to pass and closure. A closure actually is a pointer to a function that will handle it for an error handling routine in that the normal routine can call when you run into trouble. So actually, you are passing a function into your own function to allow the program to handle it. In fact, all of the try, catch, and finally block can be implemented in your own language without using the mechanism that provided for exception handling. So these are 3 different ways of working around. First, let's look at one unhandled exception. You have normal flow of execution of the program, and then something happened that you have exception that may stop your program. So you need to have some workaround, alternative way to continue the flow of the program. We call it the exception handling. But right here, we have one example that don't have this exception handling. Basically, this program have an array that have 5 elements. So the index from 0 to 4, and then we try to traverse this array up to the index 5, and that will create trouble and have the array index out of bounds exception. So let's look at this program. So right here, I have this Java program unhandled. And this is the program. It is as shown in the slides. Let's run it. Typical error that you will see is such a exception warning or actually error shown in your compiler. I'm sorry, in your IDE environment. You may be curious why I love this BlueJ so much and I'm not using Eclipse. I have the full-blown Eclipse system, but actually this BlueJ is easier to use for educational purpose because, for example, this code, they have the color. So I know this is a photo and this is a main method. So this shown the levels better for me, especially for the educational purpose. And beyond that, besides that, actually, I have the class diagram, actually like UML. So if there is certain inheritance or the use relationship, I can compile it, I can edit it real quick and then show to students. So that's the purpose why I use this. And besides that, actually this BlueJ had a built-in Java compiler that is independent of my compiler that is in the Eclipse. In the Eclipse, I have different compiler, but this one is a built-in compiler, and actually this editor is very lightweight. It's just as light as your notepad, so it's quite useful. And besides that, I can convert to the the doc file real quick. So I just click this documentation and source code transit. It is very fast. So usually this is a good tool for educational purpose, and it is also a good tool for fast prototyping. Anyway, this is an example for the exception. Let's go back to our slices. The second program I would like to show is the unchecked overflow. So right here, I have a main program. I set A to be 6, B to be 0, and then I will print now. I am in pre-division part, and then I do the division. I pass two numbers into this function division. So I convert A into double format divided by B. So this result should be a floating point number. And this is a division by 0 case. So it will create an overflow. But actually this overflow problem is unchecked in Java environment. That means Java compiler won't check for this. And unchecked exception, I'll talk about it later. But unchecked exception, actually the compiler for Java, actually it doesn't enforce you to check for the exception. So I will execute this, and then the division by 0 will happen. And after that, the value assigned to C, and I print this. I'm in after division. And then the number being printed, it will show up as infinity. That's the result that you will get from the Java environment. And then I print now I'm at the end. Okay, let's look at the code. So I clean up this output window, and then this no exception case. I'm sorry, let me open it first. So this is the code for no exception. Basically, it is unchecked and unhandled. So let's run it. So it show up like the slice. So what the problem with this this program will be, it is unchecked, so the error was shown, and it is not handled. So the programmer need to be responsible for this. But actually, there's no mechanism to help you to detect it. And compiler, Java compiler doesn't enforce it. So there's a problem for this kind of error, but it is acceptable to Java, and actually the infinity that is shown, you can handle it if you know how to do it in your program. So let's return to the slides. Now let's look at the third handled user-defined exception. Because we don't want that situation to happen, so we need to use the try catch block in Java. And because this situation is not checked, so we actually try this call before the division, after the division, and then we put a call here, and it call this division, but this time we will throw the exception using the exception mechanism in Java. And when we throw it, we create a new exception that is division by 0 created by myself, and it's defined by myself. And then if b equals 0, then we will print this out. And then we still will execute. Actually, we will not execute this return statement. You will be jumping out here and not this here, but you will jump into this because it's throw the exception, and the exception being thrown on this line, the whole thing will be break, and then this exception will be catched by this catch block, and then you will print out I'm in the catch block. After that, the program print out C, but C right here, this C doesn't have definition, so it will be this C over here that is initialized to 0. So it will print out C equals 0 and then print out I'm at the end. Now let's look at the program. So the program is right here, same as the slides. Now let's run it. So it shows up like the slides. So this program actually has a unchecked, this is unchecked exception, but it is handled, unchecked but handled. And this exception mechanism is user-defined, that's defined by myself. So this is an unchecked and handled exception. Let's return to the slides. So basically, this program, this function division will throw an exception, and this exception is an outgoing exception object. It's just like an outgoing parameter. So you pass this out, and then this division function is this one. This try block and this statement to call it. And then when we execute this b equals 0, then we will throw this exception and through this outgoing exception object and try a exception error propagation method to will be catched by here. And then it will print out this I'm in the catch block, and then it will not continue from here. It will continue after the catch block, and we'll print out this C over here. So in Java environment, we have checked and unchecked exceptions. For checked exceptions, it is not a subclass of runtime exception. The division by 0 is a runtime exception, and null pointer is a runtime exception. So runtime exception is all unchecked exception. Hardware value errors is also unchecked. Unchecked means your compiler won't handle it. The blue one, the throwable, the exception, this IO exception, SQL exception, anything related to format or IO is checked exception. For this check exception, if not caught, method must specify it to be thrown. So basically, the compiler will enforce you to store some exception to handle it for errors that programmer cannot directly prevent from occurring. So for those file IO or file not found exception, you cannot the programmer cannot prevent it from occurring. And it is not yes or no question. It's actually you will know that this will be happening somehow. And runtime error, something like index out of bound issue, actually the programmer can prevent it. Division by real, actually the programmer can prevent it. But these checked exceptions usually are file IO. For example, I open a file, I didn't know that whether somebody already deleted or not, or I search from internet and I try to reach some page, but those pages may not be existing. Then those errors actually the programmer have no way to prevent it from occurring. These are the checked exception in Java. Unchecked exception is a subclass of runtime exception, or it is an error reported by the hardware or system. If not caught, the method may specify it to be thrown. And may means that you have the option to report it or not reporting the exceptions. For errors that programmer can directly prevent it from happening. And these are the runtime exceptions. Now we'll start part 2 for this exceptional handling. Try catch finally block. Try catch finally block actually nowadays is a standard for most of the modern languages. And C++ try block is over here. Basically, this is a pseudocode, not actually C++. But you have a try catch block, and you can put if something unexpected, then I will throw my exceptions. And something here will be executed only if everything is okay. If not, this part under the exception throwing mechanism will not be executed. Then the program will be from this throw, go to this catch block if it is catched, and then it will print out oops. And on the right hand side, the blue one show you the normal execution flow. You actually put your call, the normal call over here, something that you will execute in the normal path, you put into this try block. And if something wrong happened in this try block, then you need to report the exception by throwing a exception, and that exception will be catched by one of these exception handling routine. But sometimes it may not be catched if you do not write it correctly. So the way to write this exception usually is, let's go back to the previous slides. It usually is in your try block, you should write something like exception E, and all exception will be caught by this one. So basically, you should try something of narrower definition like IO exception or SQL exception on top of this. So they will be catched first before this exception E be catched. And you need to actually write it in that way. And with this exception E, all of the exception will be catched and be handled here. But you should try something else above this catch statement. So here are the catch clauses, and you need to write it carefully. And then actually, if your code is correct, nothing happened. For the blue flow, you will jump to finally, and then wrap up the try catch block with proper handling. And then after that, you go to false. So blue one is the regular control flow. The red one is the one with exception. So right here, you try the call, maybe open the file, and if there is certain exception, it will be reported to this catch block. And if it is caught, then we execute the call in that catch block. And then after that finish, you go to finally. So finally is used to clean up. For example, some of the code in the this try block may not be finished, and actually some of the memory you may have already allocated. So in finally, usually it is used to clean up whatever happened in try block, catch block, and not actually making the system integral. So you actually can handle it here to clean up or to free some memory in this finally block. And then after that, you all go to this the call after the finally, and then we return to the normal execution flow. Propagation of an exception out of a code routine. So on the left-hand side, we have a try-catch block. And on the right-hand side, we have a full function. So actually, you don't need to throw the exception in this try block. You can put that exception throwing mechanism in the subroutine that you call. But if it happens, here you don't have the handler. So we will have a mechanism called propagation of exception out of the code routine. And then that exception will be reported to its parent or its grandpa, and then to handle it. So we will show this later, but here we call it propagation of exception. So to define an exception in Ada, we actually use this declare empty queue and exception. Modular 3, you declare as exception. In C++, we have a class. We define this as a, this is a declaration without implementation, this empty queue. And you can also declare it with parameter. For example, we have a class like this, and there is a item, duplication item. This actually is an element inserted over here. So we can throw this class, this object, with the parameter d, and we can have a constructor to assign this d to this duplicate data field. So this is the exception object that defined in C++ language. Error propagation. Right here, we have a more complete version of the pseudocode for the try-catch block. So right here, in the try block, we try to read from a file, and this code over here try to read something from a file. Potentially complicated sequence of operation involving many code to the I/O string routines. So right here, you have many I/O operation, but these statements may report exceptions. So we use the catch block. If it is end of file exception, we do something here. If it is a I/O error, say your hard disk is gone, and something like that, it will be reported over here. And at the end, you can write all kind of exception handling routine over here in the catch block. In this case, the triple dot ellipsis is a very C++ token. It does not indicate a missing call. Actually, here, the handler for any exception not previously named. So this actually, the triple dot is a very keyword or call over here. Don't actually just treat it like, okay, the author omits something. So be careful about this. And in the ML language, we have the exception handler, that this function will handle such overflow type exception, and actually will return this maximum integer back to the main program. And right here, we have handler for exceptions. So we have a try block, and you put your try block call over here. And then you have some call that's after the exception. So if the exception happen, say we are in the, say this is main program, and we have f function 1, and this function 1 inside here, you may call function 2, and then function 2 may call function 3. So your function push into the call stack, it will stack up. And your try block is the normal flow, execution flow, and your function 3 may throw an exception, and once it throws exception, it will be propagated to its parent to see if there is a handler. If not, it will go to its grandpa. Say in F1, it may handle the exception generated by F3. So actually, this try block will go to the function that it call, and maybe many layers. But if some of them happen to have some error, it will be back propagating back to its parent to see if there is a exception handler. If not, it will go to the grandparents. So right here, this is one example that you have this F3 to throw an exception, but it may be handled by F2. And then if it is handled by F2, F2 need to have a catch block to handle it. And after that, we had a finally block. So here is a Java exception propagation example. If you do not write any handler, then your exception may return to its parent, and then grandparent, and then to the main program, and maybe still unhandled. And so there are certain exceptions that are unhandled. So right here, we have the exception propagation demo. Basically, you have a main method over here, and then you try to call method 1, and method 1 call method 2, method 2 call method 3, and in method 3, a error happened because we assign a null pointer to the string, and this string is null, but we try to calculate the string's length. So this creates a trouble that exception handle occurs. So exception occurred at method 3, and method 3 is top of the call stack. So you will go down to method 2, not handled, go down to method 1, not handled, and then go down to main, and in main, we will catch the execution type exception, and then we will do something over there. So actually, in this example, exception occurs in method 3, where it is not handled, so it is propagated to method 2, where it is not handled as well, and go to method 1, not handled as well, and then go to main program where the exception is handled. So exception can be handled in any method in the call stack, either in method 3, 2, 1, or main. But basically, the one closer to it will handle it first, and then go back to the normal flow in that method. But if not handled, we'll go all the way down to the bottom of the call stack. And if still not handled, then it is a unhandled exception. And that actually the system, maybe OS or Java virtual machine, will report it. So this is how Java propagate the exceptions. Finally, in Python, we also use such a mechanism, and there is finally that, for example, in try block we open the file, but no matter it actually is queued correctly or not correctly, we can have a final block that just close the file. So this finally is a good way to, this structure is a good way to handle the files. You do the file opening at try block, And then if it's not successful, or it may be successful, but finally I close the file. And in Stepup Plus, we have similar format to C and Java. We have try catch finally block. In Visual Basic.NET, we have different way of writing it. But basically, most of the modern imperative language or maneuver language, they all have similar structures. So to implement an exception, your method, when error occurred, will throw the exception and then forward the exception to its parent methods, and maybe handle, maybe not handle. If not handle, you'll go back to another layer, and there may be a layer that handles some exception, and then we will go back to the normal flow. So first we need to throw the exception. Second, locate the handler, and then pass the exception object to the catch blocks. So they are stacked exception handler. If exception match the error type, then we do something. Otherwise, we raise the exception and sort to the next layer. Multiple exception per handler, and one handler may be able to handle several errors, several exceptions. So right here, I show you the implementation of the exception. So basically, in try block, you try certain function, and if the exception happen, then it will throw the exception, and then that exception will be used to locate the catch function. So the catch actually can be written as a catch function. So when the exception, when we throw the exception, we try to match the right catch function, and if we found it, then we will be passing the control over this function to handle it. So catch block itself, you can consider this as a catch function with the parameter over here. So itself look like a function. Now I'm going to talk about the coroutines. This is another special function or subroutines, but it's different from this exception. First, what is coroutine? Coroutine are execution contexts that exist concurrently. This concurrently means actually it can be run in different control flow, but it can be single thread or multi-thread. So I have to talk about this. And this word concurrently, nowadays we all talk about multi-threading environment, but in fact this concurrent can be pseudo parallel or real parallel. It all depends on the system. But that execute one at a time, and that transfer control to each other explicitly by name. So coroutine can also be described as recursive functions, and these recursive functions are calling each other back and forth, not the return and then call another one type. It's actually can be A call B, B call A, and A call B again, something like that. So it's can be transferring the control back and forth. Coroutines can be used to implement iterators, because iterators you may run back and forth from your main program and the iterator function to have next, and then have next will be pointing to something that handled by the iterator instead of the main program. And it can also be used to implement thread, and this will be discussed in chapter 13. And as I said, thread and coroutine are two concepts. Coroutine means two cooperative routine. Thread means the execution flow. These two concepts are different, but they can help each other. And coroutine can be used to implement the thread. Because they are concurrent, coroutines cannot be in share a single step. Remember, here is single step, not single thread. So be careful. A single step you actually cannot handle the back and forth of the transfer of the control. So let's look at the next slide. So coroutine means cooperative routines. So we may have one A function, and then this yields thread. Actually, we yield the control to B function, and B function keep going down, and then it actually transfer the control to C, and C run a while, and then go back to A, run a while, and go back to B, run a while, and then go to C, something like that. So these are A, B, C are three different routines, and they call each other back and forth. And in our Ada, Java, C#, C++, Python, Ruby, Haskell, Go, and Scala, they all have the coroutines. And the first language that has coroutine maybe is Ada. So we have generator provide cooperation through the yield keyword, that's A. It basically tells IO loop to suspend the execution. Promises provide a routine schedule and run asynchronous with the IO loop. Maybe this one is waiting for some IO, and B or C will be kicked in to help. So that is called promises. And this one is the generator. Generator plus promises actually is cooperation routines, and this we call it coroutines. So coroutine usually is some routine that run alongside with your main program to help your operations. Coroutine. Like a continuation, a coroutine is represented by a closure. So closure is a code address or reference environment into which we can jump by means of non-local goto. So it's non-local. And in this case, a special operation known as transfer. So we need to have a transfer function to transfer control from A function to B function. The principal difference between two abstractions is that a continuation is a constant. It does not change once created, while coroutine changes every time it runs. When we transfer from one coroutine to another, our old program counter is saved. The coroutine we are leaving is updated to reflect that. So basically, coroutine is a continuation, and it's just like normal functions. But the problem is that coroutine sometimes may run in an unpredictable way, different from the normal A call B, B call C, and then return type calling. That is continuation, and coroutine may change every time it runs, so we don't know. It actually sometimes depends on the environment OS as well. Thus, we perform goto into the same continuation multiple times. Each jump will start at precisely the same location. But if we perform a transfer to the same coroutine multiple times, each jump may take up where the previous one label. The previous one may be somebody else. So interleaving coroutines. So right here, I have two coroutines. I have the check file system coroutine and another one update screen. So basically, we actually initialize it. For all file, we maybe read something, and then we need to report to the screen. So we call the transfer control to update screen. US means update screen. So we go to here, and then we update it, and then we may need to read something, and then we can say transfer control to file system, check file system. So we go back from here to here, keep going down, and then okay, we have some data update. We need to update the screen, so we call okay. So these two are called coroutines. Thread and coroutine. Coroutine is the control flow. We have jumping between different control flow. Thread is actually process or procedure image, and each thread may have its own stack, its own image. So coroutine is the function or conceptual function processing, and thread is a carrier. They may carry two different functions to facilitate the coroutines. So these two terms are different. So most programmers will agree, however, that threads are substantially easier to use compared to coroutine because they eliminate the need for implicit transfer operation. But some languages may not have multi-threading mechanism. So threads are easier to use compared to coroutines. And we will talk about that in chapter 13. And coroutines is a mechanism to help you to handle two functions at the same time. This contrasts a lot of extra functionality for a little extra implementation complexity. So you use the thread with more complexity, but it can be safer or more systematic compared to coroutine. Probably explains why coroutine as an explicit programming abstraction are relatively rare. But with that said, actually, in a single-thread environment, coroutine is a way to simulate the multi-threading in a single-thread environment, and it actually can implement multi-threading. So a thread of execution is the smallest sequence of program instruction that can be managed independently by a scheduler, which is typically a part of the operation system. Thread is conceptually concurrent, parallel or not parallel. So thread is a mechanism of the operation system or virtual machine that actually presented the concurrent programming, and that can be used as a carrier for coroutine to happen nicely and easier. Stack allocation, because they are concurrent, we are talking about coroutine right now. Because they are concurrent in the nature, coroutines cannot share a single stack. Their subroutine calls and returns take as a whole do not occur in last in, first out format, do not actually happen in the single stack format. But for one coroutine itself, its call stack still be valid. Two coroutines, they cannot share a single stack. If each coroutine is declared at the outmost level of lexical nesting, then their stacks are entirely disjoint. So two coroutines may have disjoint stack. The only object they share are global, and they are statically allocated. So usually the shared data is global, non-shared data or local data they put into their own stacks. Most operation systems make it easier to allocate one stack and to increase its portion of the virtual address spaces as necessary during execution. It is usually not easy to allocate an arbitrary number of such stacks. Space for coroutine is sometimes of an implementation challenge. So you need to be able to handle multiple stack allocation, and in different OS, it is actually implemented in different way. Stack allocation, we have three implementation. Number one, give each coroutine a fixed amount of statically allocated stack space. And this may overdo it, may have overflow, may be a waste because some coroutine doesn't call that much. But this is one way we implement it. Second, put the data in heap. And heap is a dynamic allocated area, and you actually, your call friend, stack friend are allocated from the heap. So everything you put into heap, even your call friend and call stack, as they are in most functional language, then the problem of overflow and internal fragmentation are avoided. At the same time, the overhead of each subroutine call is significantly increased. So there's no call stack, but you put everything in heap. Heap had the memory allocation and the free did allocation mechanism that would cost you extra time. So these two are both not perfect. So the third one mix is more, it's better. It will allocate the stack in chunks. And what does this mean? They actually combine the 1 and 2. You actually allocate certain stack area, but you can put all the object in the heap. Then it is mixed. Let's go back to the chapter 3 to look at it. In chapter 3, we have Java memory model. Let's go back to the chapter 3. Okay, right here. In Java memory model, each thread, say thread actually is handling coroutine in Java. So each thread, we have a Java virtual machine stack. But in the stack, we store all the call frame for the local variables. But those local variables, if it is a single primitive data, it is in here. But if it is not, it's a big object or record type, we call it object in Java. Actually, they are all stored in the heap. So the stack is not as big as what C language will have. It actually put in every object in the heap. And a different thread has its own stack, but the heap still store those body of the object or instance. So the call frame remain just some ages reference data over there, and each thread or coroutine in Java will have its own stack. While the bigger array, the instance strings all stored in the heap area. So the body is stored in heap area, while the reference is stored post thread. Let's go back to the slides in chapter 9. So right here, I use Java to show you this mix method. And there are several ways to mix the stack allocation, but Java's way is quite good actually. Now, here we show you another way to implement a stack. We call it the cactus stack. The cactus you can see that from this map. So we have a main program M, and then this main program M calls some coroutine A, C, B, D, and it also calls a function Q. So each branch to the side represent the creation of a coroutine. So main function actually spawns out A, C, B, D for different coroutines, and actually M spawns out B and A, and then M continues to run Q, and Q spawn out C, and in B thread B spawns out D. That's the way they spawn out. But actually, there are 4 coroutines. If these are independent, they cannot share the same stack. So these 4, each of them is a coroutine. The static nesting blocks are shown at the right. Static links are shown with arrows, so these are the static links. So when you need to refer to your parents' variable is in this static links. Dynamic links are indicated by vertical arrangement. So this who calls who a relationship will be the dynamic links. Okay, so but this actually just show you how this cactus stack used to implement or allocate the stack in some installation of the code, some implementation of the coroutines. Transfer. The transfer function is to transfer from one coroutine to another. So you can think about this transfer actually is a combination of the epilogue and the prologue in the regular function, but this actually is transferred to another coroutine, but it's different from the call and return type of the prologue and epilogue. But transfer actually act just like that. So we need to transfer to actually encapsulate the changes in the transfer function. Once coroutine call transfer and a different one return. So change the stack among coroutines. Simply change the stack pointer register, and to avoid using the frame pointer inside of the transfer itself, at the beginning of the transfer, we push the return address and all other poly save register onto the current stack. We then change the stack pointer, pop out the new return address and the other register of the new stack and return. So here are a pseudocode for transfer function, push all register other than SP, including the return address, into a certain stack. And then we assign the SP to the current coroutine and coroutine's pointer body. And then we actually argument being passed to transfer function. And then we assign the new SP stack pointer and pop out all the register or other than the SP, including the return address. If we will return from, go to another coroutine. So anyway, this is very not really clearly described, but there is a transfer function for the coroutine. And if you are interested, you need to dig into this more. And we won't spend too much time here. So we are on the last lecture for today's talk. It's on the events. What is an event? Okay, event actually is something to which a running program needs to respond, but which occurred outside the program at an unpredictable time. So an event actually is a special case that may be breaking out from your flow, or it may happen on a different thread, but you need to handle it. So the event handler is a special type function or subroutine. So today we talk about the exception. We had an exception handler that is a special function. Coroutine again is another type of the subroutine or function. And right here we are talking about event handler, and event handler is yet another kind of the function or subroutine. The most common events are input to the graphic user interface system. Keystroke, mouse motion, button clicks. They may also be the network operation or other asynchronous I/O activity. The arrival of a message, say someone writes some message on my Facebook, and I will be notified with the event. The completion of the previous requested disk operation. I try to download something, and now it complete. These are those type of the event we deal with daily on our Windows or GUI system. Each one is called an event, and when it will happen, we don't know. And it is at a unpredictable time, so we really don't know when an event will come. But one thing we do know, that is how we are going to handle it. In the I/O operations, we assume that a program looking for input will request it implicitly and will wait if it isn't yet available. This sort of synchronous and blocking input is generally not acceptable for modern applications with graphical interface. Instead, the programmer usually wants a handler, a special subroutine, to be invoked when a given event occurs. So we don't know when it will happen, but we do know something that we want it to be handled in a certain way. That is the handler that we need to write. So handler are sometimes called as the callback function. Callback function means what? Means the runtime system calls back into the main program instead of being called from it. In an object-oriented programming language, the callback function may be a measure of some handler object rather than a static subroutine. So it usually is not a subroutine in your own main class, and instead you need to write a event listener and put a handler function in there in Java's swing case. And it is called a callback function because our main program doesn't call it. It is called by the system, and the system OS will call it. And we'll show it later, okay? This is called callback functions. Now, let's first look at the event-driven programming environment. We have some keyboard or some touch screen. So we try to do something on our touch screen device, say. And then this finger gesture or finger motion being detected by the input device and sent to your operating system. And it creates certain events and put into the event queue. And event queue could be multi-threading and could be single-threading. And those event queue will be dispatched to a application program to handle it. And then it do something, and maybe you will respond to the OS and then change the content in the display. So this is the flow of our event-driven programming environment. And how are we going to handle the events? We have several different mechanisms. Now let's get started with the single-threaded event loop case. That's in JavaScript. JavaScript engine is on the browser, so it usually is operated on the client side. And in the old day, when JavaScript just get out, we are assuming that the client side need to be very lightweighted. So it doesn't have the event big multiple threading environment. Actually, it's only a single-threaded event loop. We use that to dispatch our event. So say we have mouse click on a browser or somewhere, we have input or recording or something. This event will have event emitter, say mouse click. And those events being put into an event queue and being processed by the event loop one by one. And event loop get an event, will send to event handler and then change the state on the disk or your system. So this is called single-threaded event loop in JavaScript's approach. And in the multi-threading environment dispatcher for Java, we have different event emitter or event source. And those event source will generate events. But this event queue take the event from different source, not a single thread. We actually have the multiple thread and we dispatch it into different event handler concurrently. So we will need an event dispatcher instead of event loop. It's multi-threading event dispatcher and dispatch those handler into different threads. This is in the Java's system. And in some C#+ class, especially the Qt system, we have the signal slot mechanism. And the signal slot mechanism is like we have object one that is similar to the event source. And we have object two, we can think about the event stink or the event target. So we, in the event source, we put some signal. So we create signal, and signal is carrying the event signal, and that signal will notify the event target. And on the event target side, we have a slot, and slot is actually the callback function or the event handler. So when we click on say we click on a button, and that button will update some document, say save or something. Then this button, this object processor of the Word file will actually have a save function on the slot. That's the callback function. So this is how it is implemented in Qt system using the signal slot mechanism. So we have several different ways of handling the event and handler. Let's look at the next slide. So I am using the Swings, Java's GUI Swings package example to show you. So basically, we will have an event source, say button, and we will have an event, say mouse press down, left mouse key press down. And then this event will be put into a certain queue. It will be put into certain queue. And we will set up the event listener on the button, attach it to it, and in the event listener, we will put some event handler function attached to it. So that actually keep listening to the events. So basically, they are listeners. And once you see the queue, the current one, the newest one is matching the listener, then we will initiate this event handler object. That actually in Java Swing's case is the listener. And then we do something and we show it on the window. So there are several ways of event connection. You can have the default event, say mouse click. The default event, we will have the action performed in the Swing environment. So basically, you don't need to define your listener or your function. You just need to put into the action performed function that will be able to handle it. So event handler has these different types. The first one is the default type. You have default event, you handle by default function. The name is the action performed. Second, you have a connected event, say mouse press down, mouse release, mouse drag. These actually will have that listener mechanism, and that will handle by the event type. And we can also have the custom design event. Say we will have the loop over 1,000 times, then we will have a event created, and we can create a custom defined handler. And in some system like Qt, you have the slot function working as that. And actually, sometimes you can write the lambda expression as the handler. And you can also have the callback function in the system to help you. So there are 6 different types of handler and different type of the connector right here. And when we say right here, I click the button, right? If I click a certain button, and that button actually is on a web page. Say we are talking about a JavaScript situation. So on the same button, say this button is right here, but in the web page, we may have a box or division or even a whole page. We have several levels. We have the HTML body and then ID 1, 2, 3, 4, and then there's a button. So to trace down level by level, this is called capturing phase. To find the handler to handle it, this is called a bubbling phase. It will be top down and then up, button up. So right here, I show you the execution flow for an event handler. So we have a main program, and my main program, I somehow click a mouse click. So that mouse click maybe generate a hardware interrupt, and that hardware interrupt go to our system, and say our OS, and the OS actually maybe Windows will save state, and then it will actually call a signal trampoline. And this simple trampoline actually is the event loop. So this signal trampoline is this event loop. Say if we are in the JavaScript situation or event dispatcher. So basically, you will always know that, okay, I got a mouse click, right? Then I return from the interrupt. I actually notify the web browser engine, and I have this called signal trampoline. So the engine say, oh, this is a mouse click. So I find the event handler to handle it. So right here, from here to here, actually is from the emitter, hit the hardware, and then OS report, put to the queue. And then I have this event handler finding a handler. Then I find a handler and run it. After my save of the document, I return to the trampoline, the loop, and then I go back to my main function, that's my web page, and keep going down. So this gives you how the execution flow of a event handler. And event handler is a special subroutine called by the trampoline. So there is a handler, and we need to set a handler. To set up a handler, we actually is to use these different way of the connection to attach the handler to a certain event source. So a program invokes the library routine, passing a document, the subroutine you want to have invoked when the event occurs. So basically the subroutine is a handler, and usually it's from a library routine. In practice, most handlers need to share the data structure with the main program. So the trampoline is event loop. Thread-based handler. Okay. From single thread, there is no such thing as thread-based handler. But in many contemporary GUI systems, they are thread-based. So whenever we actually create an event and we want to handle it, those handler usually is another thread. So basically, this chart, the trampoline, and create an event handler. This event handler can be single-threaded alongside of the human program in JavaScript case. But in Java's case, this event handler is a separate thread. And examples including the OpenGL environment, utility toolkit, GLUT, the GUI image manipulation program, GIMP toolkit, GTK, GTK short for this, and the JavaScript library, Windows Phones, and the newer .NET Windows Presentation Foundation, WPF. So there are several, I should say, API or package or system to handle to provide a thread-based handler. Here is a event handler in C# language. Say I have an event source pause button, and I create a button and then create a reference for the button, right? So this button actually is this button here as event source. And actually this button has one event click, and then I put the event handler to be attached with this click. So this is a event, and this is a event handler. This is connected. And this event handler actually is a object. And this handler object will have a function. The function is over here. So the handler function being declared here, and is put into a handler, and the handler attached with a certain event, and that event is part of the feature of this button. So the button is event source, and this post the click assigned with this event handler is the connection of the event handler and the source. And the event handler function is over here. Swap-based handler, here is the same handler. And this same handler can be written by anonymous delegate or as a lambda expression. So anything can be used for a function or similar to a function can be put here for the handler, especially the delegate or lambda expression. Thread-based handler, this in Java's case, Java, you create a button, put it here, and then we add an action listener with a listener object, and this listener object may have the action performed. That is the handler function, and that handler function actually can be simplified by a lambda expression. So the event source is this J button, post button, and then the connection is this add action listener statement, and then the handler is this action performed. Is under this listener object. So listener object is an event handler object, and the action performed function is event handler. And a listener can handle multiple events. So you can have this listener and put many different handler with different event defined as here. Okay, so today we are quick. We finished before 1 hour 30 minutes, and this is the second part for chapter 9, and we actually run through quite smoothly in this week. And in the future 2 weeks, actually, we also have only one chapter in 1 week. So please catch up your homework and quiz and discussion board and whatever program you actually had not finished, try to catch up. And also work on your term project. This last 3 weeks, I allow you more time to work on that. And if you have any question, just let me know. Thank you. Okay, see you next week.